Imagine a computer that could crack today's strongest encryption, simulate complex molecules to discover new medicines, and solve problems that classical supercomputers would need longer than the age of the universe to handle. That's the promise and the hype around quantum computing. But what actually is a quantum computer? Is it just a faster laptop? Is it magic? Or is it something completely different? In this video, we'll strip away the buzzwords and give you a clear, beginner-friendly guide to quantum computing. No advanced math, no physics degree required. By the end, you'll understand what qubits are, what superposition and entanglement really mean, why quantum computers are so fragile, and what they might realistically change in your lifetime. So if you've heard the phrase, quantum computing will change everything, and quietly thought, I have no idea what that means, stay tuned. Let's decode this, one idea at a time. Before we touch quantum anything, let's ground ourselves in ordinary classical computing. Your phone, laptop, and even the biggest supercomputer on Earth all work using bits. A bit is just a tiny switch that can be in one of two states, 0 or 1. Every photo, video, or app ultimately reduces to huge patterns of these zeros and ones. Classical computers are incredible at following step-by-step instructions very fast. But for some problems, like factoring gigantic numbers, optimizing massive logistics networks, or simulating complex chemistry, the number of possibilities explodes so quickly that even the best classical computer can't reasonably try them all. Quantum computing doesn't just make these old switches faster. It uses completely different rules, from quantum physics to represent and process information. That's why it can, in principle, tackle certain problems far more efficiently. To see how, we first need to replace bits with something stranger, qubits. A classical bit is simple. It's either 0 or 1. A qubit, short for quantum bit, is different. It can be in a state we call a superposition of 0 and 1. You can imagine a qubit like a tiny arrow pointing somewhere on the surface of a sphere, often called the Bloch sphere. One point on the sphere represents pure 0, another represents pure 1, and every other point is some mix of the two. Here's the key. While the qubit is in superposition, we don't say it's 0 or 1. It behaves as if it's partly both. Only when we measure it does it collapse into either 0 or 1 with certain probabilities. This is not the same as classical uncertainty, like a coin hidden under your hand. In quantum mechanics, the superposition is real. Until measurement, the system, doesn't have a definite classical state. Quantum computers exploit this to process many possibilities at once. Superposition alone is interesting, but the real power of quantum computing appears when you have multiple qubits. With classical bits, two bits can be in one of four possible states at a time: 0, 0, 0, 1, 10, or 11. With two qubits, you can have a superposition of all four states at once. With 3 qubits, it's 8 states. With n qubits, it's 2n states simultaneously. This is why people say quantum computers have massive parallelism. It's not like running millions of separate classical computers, but mathematically, the quantum state encodes information about many possibilities at the same time. However, you don't get to just read out all those possibilities directly. Measurement still gives you only one outcome per run. The art of quantum algorithms is designing sequences of operations, quantum gates, that nudge these superpositions so that the correct answers are more likely when you finally measure. Now let's talk about the weirdest ingredient: entanglement. When qubits become entangled, their states are no longer independent. Instead, they form a single shared quantum state. Measure one qubit, and you instantly gain information about the other, no matter how far apart they are. A famous example is the Bell pair. You prepare two qubits so that, until measured, they're in a superposition of both are 0 and both are 1. When you finally measure them, you'll always get matching results. 0, 0, or 11, but never 0, 1, or 10. Einstein called this spooky action at a distance, but importantly, it doesn't let you send information faster than light. For quantum computing, entanglement is crucial because it creates correlations that classical bits simply can't imitate efficiently. Many quantum algorithms rely on carefully building and manipulating entangled states to gain their speedups. To compute, we need to change qubits in a controlled way. In classical computers, logic gates like AND, OR, and NOT act on bits. In quantum computers, we use quantum gates, precise physical operations that rotate and entangle qubits. Think of a single qubit gate as rotating the arrow on the Bloch sphere. A Hadamard gate, for example, takes a qubit from a definite 0 or 1 into an equal superposition of both. Multi-qubit gates, like the Sianot gate, create entanglement by flipping one qubit depending on the state of another. A quantum algorithm is basically a carefully designed sequence of these gates. You start with qubits in a known state, apply a circuit of gates, and then measure. The trick is to choreograph these rotations and entanglements so that wrong answers interfere destructively and right answers interfere constructively, boosting their measurement probability. So how does this quantum weirdness translate into real computational advantages? Not every problem gets faster with a quantum computer, but for certain mathematical structures, quantum mechanics provides shortcuts that classical methods don't. One famous example is period finding, discovering repeating patterns in functions. Quantum algorithms can explore many inputs in superposition and use interference to reveal the period much faster than trying each input one by one. This idea underlies Shor's algorithm for factoring large numbers. Another class of advantages comes from search. Grover's algorithm can search an unsorted database of n items in about n steps, whereas classical search needs about n2 on average. That's not exponential, but for huge n, it's still a big win. The key idea: quantum computers are not general speed-up machines. They excel when problems can be mapped onto interference patterns and entangled states that amplify correct answers efficiently. Let's zoom in on Shor's algorithm because it's the one that scares cryptographers. Many of today's encryption schemes like RSA rely on the fact that factoring a huge number into primes is extremely hard for classical computers. The best classical algorithms take time that grows superpolynomially with the number of digits. Shor's algorithm uses quantum parallelism and interference to find the period of a certain function related to that big number. Once you know that period, you can efficiently extract the prime factors. On a large enough error-corrected quantum computer, Shor's algorithm would make breaking RSA dramatically faster. This doesn't mean your passwords are doomed tomorrow. Current quantum hardware is nowhere near powerful enough to run Shor's algorithm on realistically large keys. But it does mean we need new post-quantum cryptography schemes that remain secure even in a future with mature quantum computers. Another important algorithm is Grover's search. Imagine you have an unsorted list of 1 trillion possibilities and exactly one of them is correct, like a database entry or a password. A classical computer, even optimized, effectively has to check a large fraction of them one by one. Grover's algorithm treats the list as a quantum superposition of all possibilities. It repeatedly applies a sequence of gates that does two things. It flips the phase of the correct answer, then performs an inversion about the average operation. Mathematically, this amplifies the probability of the correct item and suppresses the others. After about n iterations, the correct answer's probability becomes very high, and a measurement is likely to reveal it. For 1 trillion items, that means about 1 million steps instead of 1 trillion. This is a quadratic speedup, not as dramatic as Shor's exponential leap, but still huge for certain large-scale search and optimization tasks. So what do real quantum computers look like? Most current systems use superconducting qubits. These are tiny circuits cooled to near absolute zero so that electrical resistance vanishes and quantum effects dominate. If you've seen those golden chandelier-like machines from IBM or Google, that's the cryogenic hardware holding the qubits. Another promising approach is trapped ions, where individual charged atoms are suspended in electromagnetic fields and manipulated with lasers. There are also photonic qubits, spin qubits in semiconductors, and more exotic proposals. All of them face the same core challenges. Qubits are incredibly fragile, easily disturbed by heat, vibration, or electromagnetic noise. This disturbance, called decoherence, quickly destroys quantum information. Today's devices, with tens or low hundreds of noisy qubits, are called NISQ machines, noisy intermediate scale quantum. They're powerful research tools, but not yet the fault-tolerant quantum computers needed for big algorithms like Shor's. To build useful quantum computers, we must conquer errors. Every gate, every idle moment, every measurement introduces a chance that the qubit's state drifts or flips unintentionally. Unlike classical bits, we can't just copy qubits to back them up. Cloning unknown quantum states is forbidden by physics. The workaround is quantum error correction. Instead of protecting each qubit individually, we encode one logical qubit into a carefully entangled state of many physical qubits. Specific patterns of measurements, without fully collapsing the encoded information, let us detect and correct certain errors. A leading scheme is the surface code, which arranges qubits on a 2D grid and can, in theory, tolerate relatively high error rates. The downside is overhead. One reliable logical qubit might require thousands of physical qubits. This is why you'll hear experts say that, although we have 100-qubit devices today, we'll ultimately need millions of high-quality qubits for large-scale, fault-tolerant quantum computing. With all these limitations, you might wonder, can we do anything useful today? The honest answer is, we're in the exploratory phase. Researchers are testing quantum advantage, or quantum utility, on specific tasks where NISQ devices might outperform classical methods. Promising areas include simulating small quantum systems, like simple molecules or materials, because nature itself is quantum. Early experiments have modeled basic chemical reactions, hinting at future applications in drug discovery and materials design. Other candidates are optimization problems in finance, logistics, or machine learning, where hybrid algorithms combine classical and quantum resources. It's not yet clear how big the practical benefits will be, but companies and governments worldwide are investing heavily to find out. Think of today's quantum computers like 1940s vacuum tube machines. Noisy, limited, but historically important. We're learning the engineering and the algorithms that future generations might take for granted. If you want to get hands-on, you actually can, right now. Several companies offer cloud access to real quantum processors. IBM Quantum, for example, lets you design circuits using their Qiskit framework and run them on real hardware or high-fidelity simulators. Other platforms include Rigetti, IonQ, and Amazon Braket. You don't need to be a physicist to start. Basic linear algebra helps, but many tutorials focus on intuition and visualization. You'll learn how to create qubits, put them in superposition, entangle them, and measure outcomes. You'll see firsthand how noise and randomness affect your results. Even if quantum computing never touches your day-to-day job, understanding it gives you a huge conceptual advantage. It's becoming part of the technological literacy of the 21st century, like knowing what an algorithm or a neural network is. Exploring today, while the field is young, puts you ahead of the curve as the hardware and applications mature. Let's quickly recap the core ideas you've learned. Classical computers use bits, zeros and ones, to process information step by step. Quantum computers use qubits, which can exist in superposition, representing combinations of 0 and 1, and can become entangled, forming correlations stronger than anything classical. Quantum gates rotate and entangle these qubits, creating interference patterns. Clever algorithms use that interference to amplify correct answers and suppress wrong ones. Shor's algorithm threatens current encryption by factoring big numbers efficiently. Grover's algorithm speeds up unstructured search. Real quantum hardware today is noisy and small-scale, using technologies like superconducting circuits and trapped ions. To reach truly powerful machines, we need robust quantum error correction and millions of high-quality qubits. Right now, researchers are exploring chemistry simulations, optimization, and hybrid quantum classical approaches. We're early, but the foundations are in place for a new era of computation built directly on the laws of quantum physics. If this walkthrough made quantum computing feel a little less mysterious, don't let it stop here. You now have the conceptual toolkit to go deeper. Next steps. Explore interactive visualizations of qubits and block spheres. Try building simple circuits on a cloud quantum platform, or dive into beginner-friendly courses on Qiskit, Cirq, or quantum information basics. Even an afternoon experimenting with real quantum hardware can turn these abstract ideas into something tangible. On this channel, we'll keep unpacking complex tech, quantum, AI, and beyond in a way that's rigorous but human. So, if you want to stay ahead of where computing is heading, make sure you subscribe, hit the notification bell, and share this video with a friend who's curious about the future. Drop your questions in the comments. What part of quantum computing still feels confusing? I'll use your questions to shape the next deep dive in this series.